Welcome to data analysis and hypothesis testing. So here is ways to test data related questions. First one would be using descriptive methods. So in using descriptive methods, we would be able to, for pandas, use data frame.describe methods. And what that returns is it returns count, mean, standard deviation, min, uh, the first quartile, second quartile, and third quartile, and maximum value. So count represents a number of data. So if we look at example, you can think if say your stakeholder asks how many active users do you have this week, then that will be you'll be interested in looking at count as a number of data. And if mean is an average column value, so for example that you see, it's a sum of 10, 20, 30, 40, 50, 60, and divided by count, which is 6. So you can think of the intuition for the mean is center of gravity. And the example question could be how much money users are spending on average this month, next month. Now, if we look at standard deviation, STD is a shortened abbreviated version of standard deviation. It is a measure of the amount of variation or dispersion from the mean. So this is something that uh, non-data savvy stakeholders almost never ask, but you probably want to check the standard deviation for statistical analysis, or you want to visualize the spread of the data to explain the data set to your stakeholder. So minimum, maximum values as well as boundary of each of the quartile. So you can see this visualization for from minimum to first quartile that covers about 25% of data, from first quartile to median that covers 25% of data, median to third quartile 25% data, third quartile to maximum 25% data, so on. We will cover more when we get to data visualization, but you can often use box plot to show the quartile and check the distribution of data, etc. So for descriptive statistics, we need to talk about box plots. So box plot is a robust and resistant graphical technique for examining assumptions such as normality. Normality you can think of as symmetry in how the box looks, and equality of variances. And these graphics also provide a visual assessment of the effects of a transformation, which will become one tool we can use when dealing with violations of assumptions. So box plots, in order to create one, require knowing median, which is the line in the middle, and the first and third quartiles, and also smallest and largest values. So we talked about descriptive methods. Now let's move on to correlational method. To understand advanced machine learning analysis, it is really important to understand the basic correlation first. So for correlation, you can think of it as a relationship between more than two things. It's often called as bivariate relationship. You when we talk about correlation, we are mathematically showing if those two things, the two events are moving together or not. Yeah, we'll delve into more, but know that it can also mean that how well if we have two events, how well either one predicts the other. Here are some examples of claims from correlational analysis. So the value of X predicts the value of Y. X and Y are related. X and Y are correlated. X and Y go together. When you hear claims like this, you want to think about correlational analysis. But really important thing you want to know is that this does not mean X caused, increased, or decreased Y. So causal inference is for experimental method. You can never make a causal inference. Now let's look at some examples. So our goal is to check the relationship between X and Y. Let's say X is foot length and Y is height, and we have sample size of 20. And suppose we wish to graph the relationship between foot length and height of 20 subjects. In order to create the graph, which is called a scatter plot or scattergram, what you do is you basically uh, put a dot on a subject with matching height and foot length. So if subject's height is 70 and foot length is 10, you want to mark dot uh, in where y is 70 and foot length is 10. So this, as you see, yeah, you just want to place a dot at the intersection, and the example shows a height being 70 and foot length being 12. So you would want to definitely do this for all 20 subjects. Once you do that, so here's another example. Find 8 inches in x-axis, find 62 inches in y-axis, and place a dot. And let's say this is the scatter plot of all 20 subjects. Then you might see a pattern here. As you can see, as x foot length increases, what happens to y? Y also tend to increase, or you can say as height increases, x value foot length tend to increase as well. So this pattern can be described in a couple of ways. We can say if the points on the scatter plot has an upward movement from left to right, then we can say the relationship between those two variables is positive. So for our example, we can say that there is a positive correlation between foot length and height. If the points on the scatter plot have a downward movement from left to right, as shown in this example, then we say the relationship between the variables is negative. So let's go more into a positive correlation. A positive relationship means that high scores on one variable are associated with high scores on the other variables. It also indicates that low scores on one variable are associated with low scores on the other variable. And a negative relationship means that high scores on one variable are associated with low scores on the other variables. So it indicates that low scores on one variable are associated with high scores on the other variable. So we looked at positive and negative correlation. You might also run into weak correlation. We say it's weak correlation when these dots are too spread out so that low scores on one variable are related to both low scores on the other, both low and high scores on the other variable. So for example, we see X value is, I'll say here is about zero point 0.3, and it is related to Y value being almost -1, but at the same time, Y value is almost like 0.8. So we don't really see a uh, clear trend. And when we have a scatter plot looking like this, we would say it has weak correlation between two variables. So how can we tell if two variables are associated? So we need to talk about this, the Pearson correlation, R. It's basically a statistical test used to assess whether or not a correlation is statistically significant. So it's you can think of this as a mathematical expression of the relationship, and the value will be between -1 and 1. And this sign indicates direction, and the number indicates the strength. So negative means there's a negative relationship. Positive means there's a positive relationship. So the closer the value is to -1 or 1, it means the stronger the relationship it is. So if you look at this example of correlation coefficient of R 0.9 or correlation coefficient R negative 0.99, you can see that the relationship looks really strong. On the other hand, when we have our small r value 0 or negative 0.3, we don't see a strong relationship. We see like a weak relationship. And you can also think of it as if scatter looks tighter, then it yields higher correlation, and the diffused scatter yields a uh, low correlation. Just remember that the coefficient of R cannot exceed -1 or +1. So let's look at R equals 1 plot, which is basically almost a straight line. So we can see that the more closely the points cluster toward a straight line, the stronger the relationship is. Here's a graph diagram that shows strength of correlation. So one thing you might ask is how much of a value does it have to be to say it's a two value two variables are strongly correlated, or what should the R value be in order for us to say two variables are weakly correlated? It will depend a lot on the sample size, but this is a rule of thumb. So if we want to say two variables are weakly correlated, if the value is between uh, zero point 0.1 through 0.3 or -0.1 through zero point 0.3, it's weakly correlated. We would say strongly correlated if the value is between 0.7 through zero point 0.9. Same with -0.7 to zero point 0.9. But this is a sort of rule of thumb, so you should take this with a grain of salt. We need to be careful with outliers because an extreme value that has a outlier has a big leverage on the correlation, especially when sample size is small. So as you can see from this example, if we have, say we have R value at 0.26, if we have this outlier, it changes the R value to 0.26 to 0.37. Or you can think of it this way. Uh, this is the data we have, and this single value, this outlier, kind of changes the R value from 0.26 to 0.37. And this is more significant if you have smaller n size. You can see this one value really uh, change the relation, the correlation coefficient. So the best solution is to obtain a large sample. If you obtain a large sample, the impact of outlier on correlation coefficient is not that big. Say if that's not possible, then you would want to report statistics both with and without outliers. So strength of correlation. So when we talk about strength of correlation, we would uh, talk talk in terms of absolute value because a set of scores with R being -0.6 and +0.6, they have the same strength because both sets cluster similarly. Let's do a quick review. Out of these two, which one is showing a positive relationship? It's this one with R value being positive. And which one is showing a negative relationship? It's this one with R value being negative. For those of you who may be curious on how to calculate R, which is a Pearson correlation coefficient, uh, you would want to get the mean of X and mean of Y, as you can see here. And for each sample, say N is 20, first sample, you would want to get that sample's X value and Y value, and you want to uh, see how far that sample value is away from the mean of values in X and mean of value in Y, and multiply that and do sum of all sample values, and then you want to do a square root of the difference between the sample X with mean values in X square, and you want to sum that, and you want to do the same for Y, and then you will be able to get R value, which is Pearson correlation coefficient. So here's a mini quiz. Which option shows the strongest relationship between the two variables? So A is 0.12, B is negative 0.8, C is 0.82, D is negative 0.91, E is negative 1.1. This is can be a little tricky. Uh, although E is negative 1.1 has the highest value, we discussed that R value cannot exceed negative 1 or 1. So D would be the answer. Now indicate whether each of the following statements describe a positive correlation or a negative correlation. The more income rose among a sample of poor families, the fewer symptoms of mental illness their children experience. So when you see a statement like this, the first thing you want to do is identify two variables. What are two variables in this statement? The more income rose, so income would be one of the variables, and fewer symptoms, so symptoms would be another variable. So we're trying to see a correlation between income and symptoms. So as income increases, symptoms of mental illness decreases. So it will be a negative correlation. What about this one? As the temperature goes up, ice cream sales also go up. What are two variables? Temperature and ice cream sales. They both go up. Therefore they have positive correlation. So in order to calculate correlation in Python, you would probably look into three packages: NumPy, SciPy, Pandas. Here's another quiz. When ice cream sales rise, so do homicides. This was actually article. So we see that there's a positive correlation between ice cream sales and homicide. Do you think what do you think of this? Why do you think this is happening? Why do you think there is a positive correlation between ice cream sales and homicide? Do you think they are somewhat related? Do you think selling more ice cream causes homicide? So we mentioned in the beginning of the lecture, we said that correlation does not imply causation. So although they ice cream sale and murders have both uh, are highly correlated, there could be third variable that are related. So make sure that you really remember that correlation does not imply causation. So here's another example. Say you're an analyst analyzing patient data, and you saw that the patient with symptoms of depression reported to have low self-esteem. You could think that and that low self-esteem can cause depression, or depression could cause low self-esteem, or there could be a third variable where distressing events or biological predisposition could cause both low self-esteem and depression. Therefore, they are correlated. So here's an example of using correlation coefficient for data scientists. Say you want to find a key performance indicator for your company that are highly correlated with revenue or retention. Yeah, when you work as data scientist, data analyst, this is something that you would often do because for companies, revenue and retention, they're like two most important things. Uh, you when you want to, for this case, you can check correlation coefficient, which is the R value between KPIs. Now let's look at experimental methods. So correlation method, predicted outcome, or associate different factors. Experimental method will manipulate various factors to discover their effects. And one popular example is A/B testing. This would be something that you run into as you work as data analyst or data scientist. A/B testing is also known as bucket testing, or split run testing, or split testing. It's a way of comparing multiple versions of a single variable. So to give an example, it could be testing a subject response to variant A against variant B and determining which of the variant is more effective. So if you look at this picture, this is doing A/B test on users who visit a website. So we have two variants. Variant 1, option A, has blue UI component on the right top. Option B has red UI component on the right top, and we want to see uh, how likely this will lead the retention of the visitors, or how likely this will uh, lead to any purchase. So you'll find out by splitting visitors into group A and group B. we'll find the effect. So 17% could be uh, how long, what's the percentage of people stayed in the site for longer than 10 minutes, or it could be something like 17% of the visitor eventually purchased within, say, 2 weeks. So we we're doing experiment. So what we mean by experiment is a method in which researchers vary one or more factors to observe the effect on some behaviors. And when we do this, it is uh, really important to do a random assignment. What we mean by random assignment is assigning participants to experimental and control groups by chance. So control group for the context of A/B testing that we saw would be option A. Experimental group would be option B. So option A might be the current site, how the current site looks. Option B might be the new design that they're testing. By assigning participant by chance, we are minimizing any pre-existing differences between the groups. So visitors might have different demographics, different gender, different age. So by assigning randomly, we try to minimize these pre-existing differences. And another thing that is really important in experiment is double-blind procedure. This is a procedure in which not only participants are ignorant about whether they are in group A or B, but also the researcher is ignorant on whether the participant is in group A and B. This way, it it eliminates any bias that can happen. So we under we looked at the two what experiment is and two important thing about uh, setting up an experiment. Let's learn about hypothesis testing, p-value, statistical significance, which will be null hypothesis significance testing. And a lot of times you will see it as NHST. So when do we use null hypothesis significant testing? That's when you want to tell whether there is a significant difference between groups or not. So say your company did A/B testing and the control group with a red component showed 23% of purchase after a week, and the variation group B showed 37% of purchase after a week. Then how can we tell whether uh, this group B had more purchase because of this change, or if whether it's just a fluke? Then to tell that, you want to use null hypothesis significant testing. So there's a procedure. So the null hypothesis significant testing begin with an assumption called the null hypothesis. So null hypothesis is assuming that there is no effect, and we are trying to test the difference between two conditions. So step one, assume that there is no effect. And step 2, collect data and calculate your results. Step 3, calculate the probability of getting a result of that magnitude or one even more extreme. If the null hypothesis is true, step 4, decide whether to reject or retain the null hypothesis. We will go more into detail step by step. So step 1, if we were to use that A/B testing example, what we mean by assume that there's no effect, we're assuming that there is no difference between group A, condition A, and condition B. So the A/B testing that we looked at, having red component, blue component, that doesn't make any difference. Step 2, collect data and calculate your result. So you want to calculate the mean and standard deviation from each group A and B. And the example we saw, the results show that for A is 23%, B is 37%. And now the third step, you want to calculate the probability of getting a result of that magnitude, or one even more extreme if the null hypothesis is true. So we will get probability or p-value. So let's talk more about calculating the probability p-value. So this would be the probability of finding a difference between A and B. We want to tell whether this difference is rare or common, and the probability, say this turned out to be 0.02, then now that we have p-value, uh, in step 4, we would decide whether to reject or retain the null hypothesis. Null hypothesis meaning if we are rejecting the null hypothesis, then we're rejecting our hypothesis that there is no difference between A and B. So that means there is a difference between A and B. If we're retaining the null hypothesis, then we are assuming that there is no difference. So it is when you have p-value of 0.02, it is extremely rare if the null hypothesis is true. So rare that we think the null hypothesis must not be true. So we're rejecting null hypothesis, and when we reject the null, uh, we call the result to be statistically significant. So when we do this 4-step, we have to decide in advance um, what we mean by how rare a result has to be in order to reject a null. Conventionally, we use p being 0.05 as a decision rule. So that is, we plan in advance that if the result we obtain in our study would happen less than 5% of time under the null hypothesis, then we reject the null. Here's an example case. So let's compare the two groups, and the difference between two groups was 0.89 in the study, and you calculate that a result would occur 20%, 25% of the time if the null hypothesis is true. So in this case, we decide not to reject the null because the p we obtained is larger than our decision point of p being 0.05. So instead, we will say we retain the null hypothesis, which means our result is not statistically significant. That's everything I have. Thank you.